So good morning, everyone, and welcome to this lecture. This is lecture number 3 in electrostatics, and we are dealing with electric field. If you remember, we had seen the electric field of some type of charge distribution, starting with a wire, a long wire. We had seen the general form of electric field for a long wire. If it is a long wire, we had seen if the point is ahead of the wire, how do you find out the electric field, what is the formula, and if the point is on the bisector, perpendicular bisector, or somewhere else, how to find out the electric field, what is the formula. Do we remember these formulae?
Yes, sir.
Then we had seen if the wire becomes semi-infinite, then one angle becomes 0, the other angle becomes 90. If the wire is infinite, both the angle become 90. This is an important formula that you must remember, 2k lambda by A. Then we had seen the electric field at the center of a ring. At the center of the ring, the electric field is 0, but at any point on the axis, electric field is not 0. If the ring is positively charged, it will go away. If the ring is negatively charged, it will come towards. The maximum electric field is at the distance of r by root 2, and the answer is 2 by 3 root 3 k q by r square. Remember all these results because I am seeing in this session questions are coming straight away from all these concepts. If we have a part of a circle, a circular arc, this is the electric field due to the circular arc at the center of the circle. If it is a semicircle, the angle theta becomes 180 degrees, and therefore you have the other answer. We had also seen the electric field due to a disk. This is the electric field due to a disk at the point which is very close to the disk. The value is sigma by 2 epsilon naught, and remember this sigma by 2 epsilon naught is a very important result because this is the electric field due to a infinite sheet. Did I tell you that? Yes or no?
Yes, sir.
Any sheet, if the point is very near, it becomes an infinite sheet, and the electric field becomes sigma by 2 epsilon naught. Any formula that we are doing for electrostatic field is also valid for gravitational field. What you have to understand
Yes, sir.
is 1 by 4 pi epsilon naught, which is k is nothing but equal to g. So you put in place of k, you put g, then the formula becomes a formula for gravitational field. We had also seen the electric field due to a conducting sphere or a shell. Shell can be conducting as well as non-conducting. The charge, if you give to such a body, will only come on the outer surface. Electric field inside and at the center it is 0. It is maximum on the surface and then it decreases. If you take the example of a non-conducting sphere, that was the last thing. Non-conducting sphere, the charge comes inside the sphere also, and it is directly proportional to r. This is a very important result. It is directly proportional to r. So inside it is a straight line, and then it is maximum on the surface, and then it is decreasing as inversely proportional to r square. Do we understand this? Do we remember this? Yes or no? No, yes.
Yes, sir.
Then there is a this was due to full sphere. If you have a hemispherical charge body, hemispherical shell, then what is the electric field? I will give you the formula for that one as well. Shell hemispherical shell. So write the next heading, hemispherical shell. Hemispherical shell. When I say hemispherical shell, it means the charge is only on the outer surface. Do we understand this? Yes or no?
Yes, sir.
Shell means charge is always on the outer surface. So if you have a hemispherical shell like this, the electric field at the center, oh, remember, this is a hemispherical shell, charge will be only coming on the surface, and the surface charge density is given as sigma. At the center O, electric field at the center O is given by sigma by 4 epsilon naught. Remember, it's a very important result that you should not forget. Hemispherical shell, electric field at the center of a hemispherical shell. Electric field at the center of a semi-spherical shell. So note it down, please. I'll give you a minute to note it down. Then let's move ahead and let us go on and look. One more thing is left. Let us note it down as well. Okay, the next one is you can write it as conducting infinite cylinder. Conducting infinite cylinder or conducting or non-conducting cylindrical shell or conducting slash non-conducting shell. Now why I'm writing it like this? Because whatever happens for this type of charge, the charge will only come on the outer surface. Do we understand this?
Yes, sir.
Charge only comes on the outer surface. The charge only comes on the outer surface of it. The charge only comes on outer surface of it. Now, the charge only comes on outer surface. The charge only comes on the outer surface. So, electric field at any point inside, electric field at any point inside would be zero. Do we understand this?
Yes, sir.
Electric field at any point inside would be zero. Then electric field on the surface is given by this formula lambda by 2 pi epsilon naught r. You can write it like this on the surface. Let me write it as capital R, where capital R is the radius of this circle. Capital R is the radius of this circle. Or you can write it as 2k lambda by R. As you can see, this formula is similar to the formula of electric field due to an infinite wire. Yes or no? 2k lambda by A.
Yes, sir.
So infinite hollow cylinder or infinite conducting cylinder, it behaves as a infinite wire. Do we understand this?
Yes, sir.
Electric field at any point outside can be written as lambda by 2 pi epsilon naught into small r. Do we understand this? How it is written? This formula is exactly same as what? This formula is exactly same as electric field due to a infinite wire. Am I clear?
Yes, sir.
Are we able to understand this, or this is going above our head saying bye bye?
We understood, sir.
Sure.
Mm.
This is the diagram which you can draw. Inside the cylinder, the field is 0. It is maximum on the surface. Do you see this point? It is maximum on the surface. And outside it decreases. We understand this? Yes or no?
Yes, sir.
Everyone understands this?
Yes, sir.
Okay. I'll give you a minute to note it down. Then we can move on to the next one, and the next one would be non-conducting cylinder. You understand the difference between non-conducting infinite cylinder and the previous case? What is the difference between the two cases?
For non-conducting infinite cylinder, charge is inside also.
Charge is inside also. Well done, well done. That is the difference between the two. Charge is coming inside also, beta, here. And we will have volume charge density. Charge will be distributed inside the volume. Do we understand this?
Yes,
Charge will be distributed inside the volume, and that is what we are going to get. This is the diagram. If I call this as the axis, electric field on the axis, that is the central line, would be 0. Do we understand this? On this axis, the electric field will be 0 because it will be cancelling out from everywhere. Electric field at any point inside. Now the inside point will not be 0. It will be rho r by 2 epsilon naught. And if you compare this with the formula for electric field inside a non-conducting sphere, it was rho r by 3 epsilon naught. Here it is rho r by 2 epsilon naught. And this is the way I remember it, because I think it is easier to remember it this way. Rho r by 2 epsilon naught. If you see here, rho r by 2 epsilon naught, electric field inside this is rho r by 2 epsilon naught, rho r by 2 epsilon naught. And if I just take you back to the electric field inside this sphere, and that is what I always tell you, it is rho r by 3 epsilon naught, and that is how I remember it. This is the easier way for me to remember this. Electric field inside rho r by 2 epsilon naught for this one. Now I can write the electric field on the surface. Remember, electric field on the surface, which is this point, will be maximum, and the formula is exactly same. Instead of 3, we will have 2. Only thing that is different. So it becomes rho r square by 2 epsilon naught. Sorry, rho r by 3 2 epsilon naught on the surface, and this is the point where the electric field is maximum. We understand this?
Yes, sir.
Then we have one more point, electric field at any point outside. This will be rho r square by 2 epsilon naught r. Formula is exactly same. The only difference being instead of 3, we have 2. And this is the graph. If you look at the graph is also exactly similar. Inside it is straight line and then it decreases like this. You understand this, what we have written here?
Yes, sir.
Okay. Okay, then we will write some important points. I'm seeing that all these points are coming in the exam also. So let us note down some points. Point number 1, no point charge produces electric field at its own position. So wherever it is sitting, it is not producing any electric field at that particular point. Any charge which is given to a conductor will always come on the outer surface of the conductor, and therefore the electric field inside the conductor will be 0. Do we understand this?
Sir.
Now, electric field on the surface of a conductor, we have always seen electric field on the surface of the conductor will always be proportional to sigma. Sigma means surface charge density. So just outside the conductor, this is the conductor. Just outside the conductor, the electric field will be proportional to sigma, which is the charge density at that particular point. Do we understand this?
Yes, sir.
Now, again, this question has come in the shifts that I have seen. Two charge spheres with radius r1 and r2 with radius r1 and r2 and the surface charge density in sigma 1 and sigma 2, then the ratio of electric field on their surface will be, if you look at the ratio, it will be sigma 1 by sigma 2, and sigma 1 by sigma 2 will be inversely proportional to r if the charges are same. Do we understand what I have written here?
Yes, sir.
Okay, I'll give you 2 minutes to note this down. Everyone has noted this down?
Yes, sir.
Okay, now let me give you all these things in a tabular form. Let me just put this in a tabular form of whatever we have here. So we'll think I should be able to get. Let me put it here so that you can. So you can see these three electric field point charge. Electric field due to a point charge. You remember the formula? The normal scalar formula is kq by r square. Yes or no?
Yes.
Point charge r is a radius vector drawn, and this is the graph. We understand this graph as well. Everything.
Yes, sir.
Then we have infinite long charge. Normally in electric field, if line charge comes, it will be infinite. So I have given you the formula. Electric field in scalar form is 2k lambda by r. Yes or no?
Yes, sir.
This is the vector form written. If you want to write it in the vector form, you can write it. This is how the graph of this thing looks like. Infinite sheet, sigma by 2 epsilon naught. I have given you this formula. Yes or no?
Yes, sir.
And this is the only type of charge distribution which produces a uniform field. We understand this?
Yes,
Give
sir.
you 2 minutes to note this down. Okay, then let's move, sir. We have done up till the sheet. Now let me put the next two. I hope you can see this. This is the electric field. Okay. Just give me a minute. Take this out. Just give me a minute. I'll put the next three so that you can do it. Okay, let me put one here, then I will, because not going to come. Okay, you can note down this one, which is on your screen now. Uniformly charged ring. We have already seen it, seen the electric field due to a uniformly charged ring. Yes or no?
Yes, sir.
You also seen the graph. Just note down this graph and this one. I will put the other two in the next one. Do it fast. Put the other two in the next one. That is better. I'm not able to put it in this one. This is better. Let me know once you are done. Okay, then we'll move on to this one. The last case is uniformly charged hollow conducting or non-conducting sphere or a conducting sphere. The charge will come on the surface. Electric field inside is 0 and outside it is kq by r square. This is the graph. I think all of us remember this. Then we have non-conducting sphere which is made up of insulating material. Here electric field is inside also, rho r by 3 epsilon naught. I hope we remember all this. Yes or no? I'll give you 2 minutes to note this down fast. Do it fast. Okay, then we move on and we solve this simple problem. I think we have done a similar problem in gravitation as well. Calculate the electric field at the origin due to an infinite number of charges as shown. In the first arrangement, which is this arrangement, all the charges are positive. First charge is placed at a distance of 1 meter, the second one is at a distance of 2 meter, then 4 meter, then 8 meter, and so on. In the second arrangement, the first charge is positive, the second charge is negative, the third charge is positive, and the fourth charge is negative, and so on. There are infinite number of charges here. You have to find the electric field at the origin O. I'll give you 2 minutes. I hope you can do this. You can do this, yes or no?
Yes, sir.
I'll give you 2 minutes for that. So how are you supposed to do this? If I talk about case number 1, in case number 1, the electric field due to the first charge, second charge, or any charge will always be directed in this direction. Yes or no? At the point O, it will be going away from the origin. So all the electric fields are getting added up. So electric field net, if I talk about vectorly, is nothing but summation of EI. It is the vector summation of this. All the electric fields are going in the same direction. The direction is towards left. So if I talk about magnitude, then magnitude will be K into Q by 1 square plus K into Q by 2 square plus K into Q by 4 square and so on. So basically what I need to do is KQ taken common. It is 1 by 1 plus 1 by 4 plus 1 by 16 plus the next one will be 8 square. 8 square is 64 plus 1 by 64 and so on till infinity. This is a GP, infinite GP with common ratio 1 by 4. Can you now give me the answer? What will be the answer for this? For case number 1. Know how to find out the infinite series? So to find out the ratio of this infinite series, the formula for this infinite series, you will have 4 times kq by 3. Do you know? Do you remember? A upon, do you remember that formula? 1 AR square AR cube. So this is the answer for the first one. Can you now solve the second one? In second one, what will happen? Because of all the positive charges which are pink, electric field at the point O will go away. But because of all the negative charges which are green, electric field will come towards. So if I take one as positive, the other one becomes negative. Yes or no?
Yes, sir.
Then the net electric field in the second case, what will be the difference? The first one, let me take it as positive, kq by 1 square. Then the second one will become negative, minus kq by 2 square. The third one will be positive, kq by 4 square. The fourth one would be negative, kq by 8 square. Do we understand this?
Yes.
Again, it will form a GP, and you can easily find out the ratio of that GP is minus 1 by 4. So in this case, the answer that you will get will be 4 kq by 5. I'll give you a minute to note this down. This is the next question. You have 3 concentric shells. The inner one is the smallest, the radius is A. Then you have the middle one, the radius is B. And then you have the outer one, the radius is C. 3 concentric shells. Then you can have different types of point. For example, you can have a point which is inside this shell, point number 1. This is point number 1. I hope you understand this. Then you can have a point somewhere in between the first and the second shell. This is point number 2. We understand this. The third point could be somewhere between the second and the third shell. This is the third point between shell 2 and shell 3. And then you can have the fourth point, which is outside the outer shell. You have to find electric field at all the points. The distance of that point from the center of the shell can be taken as r. So all your answers would come in terms of r, a, b, c, d, and so on. Do we understand this?
Yes, sir.
You have 2 minutes to give me the answer for this one. Again, this case is similar to the case in gravitation. Instead of giving the charge as q, I could have given the mass as m. The question remains same. So how are we going to do this? When I look at the position number 1 here, this point will lie somewhere here inside all these shells. Electric field due to the pink shell point is inside. It will be 0. Yes or no? Electric field due to the green shell at any point inside the shell is 0. Electric field due to the blue shell, the point red point is inside the shell, is 0. Electric field due to all the shells is 0. Therefore, the answer for this part is electric field becomes equal to 0. Do we understand this? Coming to the next point, point 2. Point 2 is somewhere here. Point 2 is somewhere here at a distance of r from the center of the shell. This distance, let me call it as r. This distance is r, point 2. Now, for the green shell and the blue shell, the point is still inside. But for the pink shell, the point is outside. So only the pink shell will create electric field. And the pink shell will create how much of electric field? The point is outside for the pink shell. It will be K into Q1 divided by R square, and that would be the electric field, and it will be going vertically outwards. Do we understand this?
Yes, sir.
Coming to the third point is somewhere here in between the two shells. Number the green and the pink one. Now this distance is given as r. Now if you look at the blue shell, for the blue shell the point is still inside. So blue shell cannot create field. Only the two shell, the green and the pink one will create electric field. Both electric field will be same. So the final answer for this one will become K by R square multiplied by both the shells are also having positive charges. So it becomes Q1 plus Q2. If one was having negative charge, it would have become Q1 minus Q2 or Q2 minus Q1 depending on which charge is more. Do we understand this?
Yes, sir.
When the point comes here, it comes outside all the three shells. So all the three shells are going to create electric field. Now the final answer becomes K by R square into Q1 plus Q2 plus Q3. Do we understand this?
Yes, sir.
So these are the answers for this particular question. I'll give you a minute to note it down.
Done, sir.
This is a question for you. Two concentric, uniformly charged spherical shell, R1 and R2, R2 greater than R1, have total charge Q1 and Q2 respectively. Find an expression of electric field as a function of R for the following positions: small r less than R1, small r between R1 and R2, and small r greater than R2. I'll give you 2 minutes to give me the answer. So, what are the answers? For case number 1,
Equals to 0, sir.
case number 1, when R is less than R1, then the electric field has to be 0. Yes or no?
Yes, sir.
Case number 2, when R1 is less than or equal to R is less than or equal to R2, then the electric field will be created by the inner shell only. So the answer would be
KQ1 by R square.
KQ1 by R squared. Case number 3, when R is greater than or equal to R2, then your electric field will be created by both the charges. So I can write it as K by R square into Q1 plus Q2. Do you understand this? How this is done?
Yes, sir.
Okay. Chalo. Now if you can do this one. The diagram is not given, but I will give it to you so that you can give me the answer quickly. This is the next question. Find the force acting between two shells of radius R1 and R2, which have uniformly distributed charges Q1 and Q2, and distance between their centers is R. I'll give you a minute to give me the answer. So, how do we solve a question like this? Well, remember, both the spheres are far away from each other. What we can do is, for if you look at from one sphere to the other sphere, both of these spheres for each other, they are acting more as point charges, because we have seen the electric field outside the sphere, outside the shell, is always same as electric field due to a point charge at the center of the shell. Yes or no?
Yes.
You've seen that in the formula, yes or no? So basically we can treat this question like this. There is one point charge here and there is one point charge here. This is having a charge Q1 and this is having a charge Q2, and the distance between the point charges is R. So what is the force acting between these 2 point charges? It will be simply equal to K Q1 Q2 by R square, and that will be the answer for this case. Do we understand this? That is how we can find the answer for this case. We get this?
Sir.
Okay, shall we move ahead?
Yes, sir.
Okay, let us move ahead and move on to the next question. And the next question is like this. You have two line charges. One is having charge density of plus lambda, that means it is positively charged, and the other one is having a charge density of minus lambda, that means it is negatively charged. They are separated from each other by a distance r, as you can see. There is a point P at the center of these two wires. You have to find the electric field at the point P, which is at the center of these two wires. You understand the question? Both the wires are infinite. I'll give you 2 minutes to give me the answer. So how are we supposed to do this? This is on the left hand side you have a wire which is positively charged. If I call this as the pink wire, it will create electric field in the outward direction like this. How much will be this pink field? Anyone can tell me how much is the pink field created by this charge?
2k lambda by r.
So electric field, let me call this as E1, 2k lambda by the distance r, and the distance r is actually r by 2. So r by 2. This is the electric field E1. If I call the other wire as the green wire is a negative wire. It will create electric field in the direction towards it. Towards it means it will be like this. How much will be this green field equal to? 2k lambda divided by r by 2. Both of the fields are in the same direction. They are going to get added up. So the net electric field in between these two will become how much? 8k lambda by r. That is the answer that we're looking at. I'll give you a minute to note this down. Let's go ahead and solve the next one. Have you understood this question? Yes or no?
Sir.
Okay. Here comes the next one. And the next one is like this. Now, diagrammatically, they might look similar, but you have to understand what is the difference between them. And the question comes now. Now, again, these are two infinite, but these are not two infinite wires. These are two infinite sheets having charge density plus sigma and minus sigma. Then I have 3 points here, point A, point B, and point C. Remember, these points are very near to the sheet. And remember, an infinite sheet creates uniform magnetic field. Yes or no? Do we remember this? So now I have given you 3 points and you have to tell me the electric field at the 3 points, point A, point B, and point C. I'll give you 2 minutes to give me the answer. Have you understood the question? Yes or no?
Yes, sir.
2 minutes you have to give me the answer. Yes.
Sir, at 0.80, because the direction of flow is not towards A.
And at point C? If I call this one as the pink charge and if I call this one as the green charge, the electric field at point B or any point in between due to the pink charge electric field at any point in between due to the pink charge. What is happening here? due to the pink charge will be going like this, yes or no? And due to the green charge, it is towards the plate, so it will be going like this. So both of the fields are going to get added up. Outside, due to the pink charge on the left side, the electric field, what I am doing here, the electric field always goes away from a positive charge, so the pink field outside will be like this, yes or no? It always goes away. For the green charge, the field is always towards, so it will be always like this. Do we understand this?
Yes.
So outside, whether it is at point A or whether it is at point C, both the fields are equal, but they are opposite in nature. Do we understand this?
Yes, sir.
So outside this will cancel, outside this will cancel, but inside both of them will be added up. Electric field due to the pink charge is sigma by 2 epsilon naught. Electric field due to the green charge is sigma by 2 epsilon naught. So in between the answer becomes sigma by epsilon naught. Sigma by 2 epsilon naught plus sigma by 2 epsilon naught. The answer is sigma by epsilon naught. Do we understand this?
Yes, sir.
That is the answer that we are looking at. Sigma by epsilon naught. We get this, everyone?
Yes, sir.
Pakka?
Yes, sir.
Okay. Now remember, whatever questions we have done for electric force, they were also a question for electric fields. Just to give you a question here. This is a question. You have got four charges. One is Q, the other one is 2Q, 4Q, and 3Q. And they're asking you what is the electric field at the center, along which direction it is directed. Apart from telling you which direction it is directed, you can also tell me the value of that magnetic electric field if you can. I'll give you 2 minutes. Everyone has noted this question, yes or no? I'll give you 2 minutes to solve this. So how are we supposed to do this? You must understand that this is the center of the square, so all the distances, if I call this distance as r, if I call this distance as r, if I call this distance as r, all the distance r are going to be same, yes or no?
Yes, sir.
And if the edge length is a, what will be the relation between a and r? Everyone can calculate this, yes or no? Yes or no? If the square's edge is a, what will be the distance of the vertex of the square from the center? You can calculate this, yes or no?
Yes, sir. Say that.
You cannot calculate the distance between r and a. R, a, you cannot calculate. Okay, now all the distances are same, and I think you can calculate the relation between r and a. The charges, if I look at the value of electric field, The electric field due to a point charge is kq by r square. All the distances are same. K is same, R is same. So electric field is directly proportional to Q. Q, the charge. Electric field due to this charge Q will be going like this. Yes or no? Electric field due to this charge, green charge at point O will be going away. Yes or no? Which field will be more? The blue field or the green field?
The green field, sir.
So green field will win. So the net field will be in the green direction. Yes or no?
Yes, sir.
Then I have the yellow charge. The field due to this yellow charge will be going in this direction because it is a positive charge at the point O. Yes or no?
Yes, sir.
Then I have this pink charge. The electric field due to this pink charge will be going in this direction. Yes or no?
Yes, sir.
Which field will win? The pink one or the yellow one?
Pink one.
One field is like this, the other field is like this, and they will be equal in magnitude because the difference in the charges is 2q. Yes or no?
Yes, sir.
So the net field will be going in the vertical direction. Yes or no?
Yes, sir.
The net field will be going in this direction. It will be along the direction of CB. So the answer is CB. And you can easily calculate the value of that field as well. Yes or no? How much will that field be equal to? You will be able to calculate. Yes or no? Have we understood this? Yes or no?
Yes, sir.
Pakka?
Yes, sir.
Okay. And I'll give you one question for you to calculate. Equal charges Q are placed at the vertices of a triangle ABC of side A. The magnitude of electric field at point A is how much? Point A is how much? If you want, you can draw a diagram. I will show you a diagram as well. Let us say this is your equilateral triangle. This is point A. This is point B. This is point C. The length of the side of this equilateral triangle is A. You have to calculate electric field at point A. Will you be able to calculate it? I'll give you 2 minutes to calculate. So that is option C. You have 3 charges placed here. 1, 2, and 3. The charge at A is not going to create any field at that point. So there are only 2 fields created. One is the pink one because of this pink charge. And remember, all the charges are Q. So you don't have to worry about the magnitude. The magnitude is same and the sign is also same. Then you have the green charge. In which direction will the pink charge create field at point A? In which direction is the pink charge going to create field at point A? It will be in this direction. Yes or no?
Yes, sir.
In which direction is the green charge going to create field at point A? It will be in this direction. Yes or no?
Yes.
Everything is same. Both the charges are same. Both the distances are same. This field will be inclined. These two fields will be inclined at an angle of 60 degrees from each other. Yes or no? If I call this field as E1 and if I call this field as E2, both E1 and E2 are same, yes or no?
See.
Yes or no?
Yes, sir.
I can write the value of E net as under root of E1 square plus E2 square plus 2 times E1 E2 cos phi. And the value of E1 is equal to the value of E2, that is KQ by A square. We understand this, yes or no?
Yes, sir.
So KQ by A square will come out. You will have 1 plus 1 plus 1. 1 plus 1 plus 1 is 3 under root 3. And the correct answer would be something like this. We understand this?
Yes, sir.
Pakka, sir?
Yes, sir.
Can we do this one question and then we can move ahead? This one. 4 charges are placed at the corner of a square as shown in the figure. The side length is 5 centimeter. You can take it as A. So you can take the length of the square as A. I just want a answer which may be given in terms of A. I will leave the calculation part to you. So you can call the distance, you can call the square length as A. You have to find out the electric field at point A. At the center of the square. Can you do that? Yes or no? In terms of A, you can give me your answer, not a problem. I'll give you 2 minutes to give me the answer. Anyways, I will do it. If you call this distance as A, let me give you a bigger diagram of this. This is the bigger diagram of the entire thing. If this distance is A, how much would be this distance from the center to here? How much will be this distance? This will be A by root 2. This distance will be A by root 2. Now, if I call the electric field due to this charge as E, the value of charge is Q, remember? The value of charge is Q, remember? All distances are same. The electric field because of this charge will also be E, charge are same. The electric field because of this charge will be 2E and electric field because of this charge will also be 2E. Do we understand this? Yes or no?
Yes.
Because of this charge, electric field will be going like this, E. Because of this charge, electric field will be going like this, E. It will be 2E. 2E in the upward side and E in the downward side. We will have 1E in the upward side, yes or no? Yes or no?
Yes, sir.
Then you have 2E in this direction and you will have 1E in this direction. So I will have 1E in the upward direction. These two E's will be inclined at an angle of 90 degrees. Yes or no?
Yes, sir.
So the net electric field E net will be equal to under root of E square plus E square. Do we get this?
Yes.
And the value of E will be equal to KQ by distance is A by root 2 का square. So this will be 2kq by a square, the value of E, and the value of E net will be 2 root 2 because 1 root 2 will get multiplied, kq by a square. That is the answer that I was looking for. I'll give you 2 minutes to note this down.
Ten to the power minus. Thank you. Distance and the distance and the ఈ triangle కి distance ఎంత తీసుకుంటారు? ఈ పాయింట్స్ వచ్చి లైన్ అయి ఉండొచ్చు. ఇది పాయింట్ అంటే
Shall I do it?
Sir,
Yes, beta.
is it 4q by a square? 4kq by a square.
How did you get it? 4kq by a square.
Okay.
Can you tell me how did you get it?
Distance is same for.
We have understood this?
Yes, sir.
Note it down, please.
Answer.
Okay. Then we move ahead
Yes, sir.
and move on to the next setting. And the next setting is electric lines of force or electric field lines. Electric lines of force, or you can say electric field lines. What is this electric field lines? Now, whenever we are thinking about electric field, electrostatic field, or any field for that matter, we are thinking of those electric field. To imagine that electric field, we draw some lines to understand how the field is going. Those lines are known as electric field lines or electric lines of force, whatever you call it. What are these? These electric lines of force, the line of electric force is an imaginary line which is drawn in such a way that the tangent drawn at any point on that line will give me the direction of electric field at that point, or if you want to call it in terms of force, it will give me the direction of electric force experienced by a positive charge which is placed at that point. Do we understand this? Electric lines of force or electric field lines are imaginary lines. That is the most important aspect. Imaginary line drawn in such a way that the tangent drawn at any point gives the direction of electric field, or you can say it gives the direction of electric force on a positive charge, and therefore it is known as lines of electric force. We understand this? Yes or no? No, yes. First listen to me, then I'll give you time to write. Do we understand this? Yes or no?
Yes, sir.
Now, there are certain points that you must remember about these electric field lines, and I will show them and also write them. Now, these electric field lines, the first thing that you must remember about these electric field lines, the first thing that you must remember about these electric field lines is that these electric field lines are imaginary, they do not exist. Do we understand this? You can write them as point-wise. These electric field lines are imaginary. These electric field lines are imaginary. Do we understand this?
Yes, sir.
They are not real. They are not real. You understand this?
Yes, sir.
Now, these electric lines of force or electric field lines, they always start from a positive charge or originate from a positive charge and they terminate on a negative charge. Do we understand this? Electric field lines are supposed to be starting from a positive charge and they are supposed to be terminating or finishing on a negative charge. Do we understand this?
Yes, sir.
For a positive charge, if there is one positive charge only, the electric field lines will start from that charge and will go till infinity, just like this. This is one positive charge that is shown here. We understand this? So as you can see, electric field lines are going radially outward. We call for a point charge, the electric field lines are going radially outward. Do we understand the meaning of the word radially outward? Yes or no? Do we understand radially outward?
Ah,
No?
we understood, sir.
Okay, let me just take this one off and probably I'll just show you a different diagram. Radially outward and radially inward. I will just take this one out as well. So that I'll show you in one diagram. That would be better. Radially outward and radially inward. This diagram might be better to make you understand that same thing. Radially outward and radially inward. We understand this now. Radially outward, radially inward.
Yes.
Radially outward, radially inward. We understand this?
Yes, sir.
Okay. Now, if you have one positive and one negative or two positive charges, electric field lines will be slightly distorted and the electric field lines would look like this. You must remember these diagram because this diagram may come as exam. How are the electric field lines going? Do we understand this?
Yes, sir.
I'll give you 2 minutes to draw these. So, electric field lines, as you can see, they start on a positive charge, they end on a negative charge. The same thing can be said in a different way. The same thing can be said in a different way. Electric field lines are always in open loops. Electric field lines can never be in closed loop. They are always in open loops. When I say open loops, that means they have a starting point and they have an end point. Starting point, starting point, starting point is the positive charge and end point is the negative charge. Do we understand this? Yes or no? No, yes.
Yes, sir.
The next point is electric field lines can never cut, cross or intersect each other. Electric field lines can never cut, cross, touch, or intersect each other, because if they do that, at one point you will have two directions of electric field, and that is not possible. Do we understand this? Yes or no? No or yes?
Yes, sir.
Electric field lines can never touch, cross, or intersect each other, because if they do, you will have two directions of electric field at that point, which is not possible. Everyone is following me? Yes or no?
Yes, sir.
Next point, we have already seen the direction, the tangent drawn to any point on the electric field lines will give us the direction of electric field. Yes or no? No, yes.
Yes, sir.
Everyone understands this?
Yes, sir.
Now, tangent to the electric field line gives us the direction of electric field, and therefore it will also give us the direction of, it will also give us the direction of electric force on a positive charge. Yes or no? No, yes. Because positive charge always experiences force in the same direction. Do we understand this? Yes or no?
Yes, sir.
Next point, first note all these points and I'll give you time to know, first listen to all these points and I'll give you time to note them down. If there is no electric field, there will be no electric lines of force. Do we understand this?
Yes, sir.
If there is no electric field, there will be no electric lines of force. If there is no electric field, there will be no electric lines of force. We understand this?
Yes, sir.
Just one more minute. Since there is no electric field inside a conductor, electric field line inside a conductor would be zero. Do we understand this? Electric
Yes.
field line inside a conductor would be zero. So from here we will move on ahead to the other points. Let us first note down these points, then we will move ahead. Let me know once you are done. The next thing that we are going to write is for a conductor. Electric field lines are always normal to a conductor. Now, electric field lines, whenever they are entering a conductor, they will be normal. Whenever they are emerging out of a conductor, they will be normal. So electric field lines, EFL, electric field lines, always terminate or emerge out, always terminate or emerge out of a conductor perpendicularly. Do we understand this? Electric field lines can never cross a conductor. They will always terminate or emerge out of the conductor. Do we understand this? Why they cannot cross a conductor? Because to cross the conductor, they will have to go from inside the conductor. Inside the conductor, there cannot be any electric field. Therefore, they cannot cross the conductor. They can only terminate on the conductor or emerge out of the conductor. Do we understand this?
Yes, sir.
For example, if you take this question, Just to illustrate this point, this is a question from the first IIT that I gave. A metallic sphere is placed in a uniform electric field. The lines of the force will follow which path? Which path will the lines of force follow? 1, 2, 3, 4. Which one?
Perpendicular. 3, sir.
The correct answer is 4.
4, sir.
They must come and they must terminate and emerge out perpendicularly. They cannot exist inside the conductor. Therefore, these two options are wrong. This option is wrong because it cannot terminate in any other direction other than perpendicular. Therefore, this option is wrong. Only option which is correct is option number 3.
4, sir.
Oh, option number 4. I'll give you 2 minutes to note this down. Then we move ahead. Now, by looking at the number of electric field lines which are leaving or terminating on a charge, we can find out what the value of charge is. If the number of field lines which are emerging out or terminating is more, the charge is more. If the number of field lines are less, the charge is less. Do we understand this?
Yes, sir.
Now you can see an example here. You can see an example here. Which charge will be more here? Charge A or charge B? Which charge will be more here? Charge A or charge B? Which charge will be more here? Charge A or charge B?
Charge A, sir.
Charge A, sir, because charge A has more line emerging out of it, but charge B has less lines terminating on it. Do we understand this? Yes or no?
Yes, sir.
The number of field lines per unit area. How many field lines are there per unit area? Gives us the magnitude of electric field. If the lines are dense, electric field is more. If the lines are rare, electric field is less. Do we understand this?
Yes, sir.
Looking at the diagram, can you tell me which point electric field is more and which point electric field is less? Yes, yes or no? No, yes.
Yes, sir.
What, sir?
E will be greater.
Which point electric field is more?
At point A, sir.
Point A electric field is more. Point less electric field is less. Yes or no?
Yes, sir.
Do we understand this?
Yes, sir.
Everyone understands this? Okay, I'll give you 2 minutes to note this down. That takes us to the next point. If the magnitude as well as the direction of electric field is same, electric field will be called uniform. Do we understand this? It's a vector, so magnitude and direction has to be same. If the magnitude is different and the direction is same, it is non-uniform. If the magnitude and direction both are different, then also it is non-uniform. You can see in option number A, it is a uniform magnetic field. It is same in magnitude and same in direction. Do we understand this? In case number B, the magnitude is same, but the direction is different. In case number C, both magnitude and directions are different. Do we understand this? Yes or no? No, yes.
Yes, sir.
I'll give you 2 minutes to note this down. Do it fast. Then why do charges attract and charges repel? We can explain it by the concept of electric field. Electric field in the longitudinal direction, lengthwise direction, they can contract. And that is why they produce attraction between two unlike charges, whereas in lateral direction, they expand, which produce repulsion between two like charges. In figure number 1, there are two opposite charges and you can see a contraction of the electric field line. On the right hand side figure, you can see expansion. Do we understand this? That is how, and that is why, and that is how we explain the attraction and repulsion between two like or unlike charges. I'll give you 1 minute to note it down. Don't have to draw the diagram. If you want to draw the diagram, draw it fast. You just have to understand the concept, okay? Then the next heading, we may not be able to understand this, but you may write this. Electric field lines give us an indication of equipotential surface. In fact, it is better to write electric field lines, EFL, are perpendicular to equipotential surface. Now, what are these equipotential surface? We will see them in the coming classes. Equipotential surface are surface which has the points of the same potential. So electric field lines are perpendicular to equipotential surface, and electric field lines always move or flow from higher potential to lower potential. These are the 2 points which probably we will understand in the coming classes. Right now, you just note them down. We'll understand them later. Then this is the next question, sir. Electric field lines are shown in the figure. State whether which point the electric field is more. Yes, my dear friends. At which point is the electric field more? At which point is the electric field more? Can you tell me?
At point A, sir.
At point A. And what is the reason for that? What is the reason for that?
Number of electric field lines are more.
Number of electric field lines are more at point A, and therefore electric field magnitude wise at point A is more than electric field magnitude wise at point B. Do we understand this? Yes or no? No, yes.
Yes, sir.
Then comes the next question. The value of charge Q1 is 12 microcoulomb. What will be the value of charge Q2? Will it be positive or will it be negative? First of all, tell me that. Will it be positive or will it be negative? This is Q1. I hope you can see Q1. This is Q1, which is 12 microcoulomb. This is Q2, whose value you have to find out. Can you tell me whether it will be positive or negative?
Q2 is negative.
Q2 is negative. That is correct. Now, can you tell me the value of Q2? Can you tell me the value of Q2?
Five microcoulombs. Minus 5.
Minus 5 microcoulombs.
Minus 5 microcoulomb is exactly correct. Remember, whatever number of electric field lines are going out, the number of electric field line is directly proportional to the charge. Yes or no? No, yes.
Yes, sir.
If you can count how many field lines are going from here, from here, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. 12 electric field lines are going out from charge 1, And how many electric field lines are coming inside charge 2? 1, 2, 3, 4, 5. Do we see this?
Yes, sir.
So Q1 by Q2 will be in the ratio of 12:5. Yes or no?
Yes, sir.
So if Q1 is 12, Q2 has to be 5. It has to be -5 because electric field lines are coming inside it. Do we understand this?
Yes, sir.
Everyone understand this?
Yes, sir.
Then one more question, a simple one here. If the number of electric lines of force from charge Q are 10, find out the electric field lines from 2Q charge. How many lines of force will emerge out from 2Q charge? Yes, my
20.
dear friends. And the answer is?
20, sir.
And the answer would be 20. Do we understand this? Yes or no? No, yes.
Yes, sir.
Everyone understands this?
Yes, sir.
Next question. Give me the answer fast. The figure shows some of the electric field lines corresponding to an electric field. The figure suggests which one is correct. Which one is correct, my dear friends? Which one is correct? Which one is correct?
Option C, sir.
Option C, sir. Option C, sir, is correct. Anyone understands this? At point A and at point C, you can see same density. So electric field at point A and C will be equal. They are very close at point A and C, but they are very far at point B. Therefore, it must be greater than B. We understand this, or this has gone above our head. Saying bye-bye.
We understood, sir.
This one, sir. Last question for this class, sir. Electric lines of force of electric field due to two charges Q, small q and capital Q are drawn. State if which one is the correct option, my dear friends. Simple answer, simple question. Simple question, simple answer. And the answer is
Q less than capital small q is correct. Positive
and the answer is
option B, sir.
option C, sir. Q, small q is positive. More number of field lines are emerging from small q. So small q is positive, capital Q is negative, and the magnitude of q, small q, is more than because more lines are emerging out. Do we understand this?
Yes, sir.
Yes, sir. Last question, sir. This is from IIT screening of last year's. Can you give me the answer for this? Three positive charges of equal value are placed at the vertices of an equilateral triangle. These are the three charges. You can see. This is charge number 1. This is charge number 2. This is charge number 3. Charge number 1, 2, 3. 1, 2, 3. 1, 2, 3. Which figure represents the electric field lines correctly? And the answer is
Option B, sir.
option C, sir, is the correct answer because electric field line cannot be in a closed loop. Here it was a closed loop. It is not possible. So the only option which is correct, electric field lines are always in open loops. They cannot be in closed loops. Here also we see one closed loop. It cannot be in a closed loop, it has to be in an open loop. This is the only option where you have all open loops and they are repelling each other, they are expanding laterally, and that is the correct option, option C. With this, we come to an end of this particular session. We are done with electric lines of force or electric field lines. In the next class, we will move ahead with more things on electric lines of force. We will move ahead with Gauss law. I'll see you in the next class. Take care. God bless all of you. Bye bye.
Thank you, sir.